Good afternoon, everyone. Welcome to our graduate seminar series. Today is my great pleasure to welcome Dr. Pham Duc Thin, who is a research fellow at our very own ATMRI. He obtained his BS degree from the University of Science in Vietnam in 2011, his MSc degree from Telecom Paris Tech in France in 2013, and finally his PhD in computer science from the University Paris Sciences and Lettres just this year in 2019. He has been working on combining machine learning and optimal control for automation planning in the air traffic management domain. His research interests include machine learning, data mining, reinforcement learning, and meta-heuristics. Today he's here to talk about machine learning-based flight trajectory prediction and air traffic conflict resolution advisories. As we all know, the increase in traffic demand has required novel and efficient conflict detection and resolution advisories. His team has attempted to learn and predict controller behaviors from data using the random forest technique. They have proposed an artificially intelligent agent that is capable of resolving conflicts in the presence of traffic and uncertainty. So without much further ado, let's put our hands together and welcome Dr. Pham.
Thank you, Piran, for your introduction, and good afternoon, everyone. So, as Piran has introduced, my name is Pham Duc Thin. You can call me Thin. And it's my honor to be here today to present to you the work of our team, the machine learning-based trajectory prediction and ATC resolution advisory. So, this is the content of my talk. The first one is the motivation. And then we will talk about three main components: the trajectory prediction, conflict detection, conflict resolution, and we will discuss on one case study. We use the conflict resolution with the learning the controller preference, and finally the conclusion. So for the motivation, in this domain, people talk a lot about the challenge of the increase of the traffic. As in the report of EATA, they forecast that in the next 20 years, the demand for air transportation will be doubled, and the number of passengers will increase and reach the number 8 billion in 2037. That puts the stress on the ATM system, and it is stress on the limited resource of this domain, the airspace and even the human resources. For us one, it's a very big question. Can controller handle more traffic and much more traffic, like double or triple the demand? One of the solutions is the assistant tool for air traffic controller. And people try to develop that one for the last few decades already. However, it's always face the same problem, the similar issues. The low acceptance rates due to the low transparency in decision-making process. And secondly, the controller don't trust the tool, so they don't accept the resolution of the suggestion. And finally, each controller may be very different in making decision when they make the decision. So it means if you give them the similar resolution or suggestion, they won't accept that one. So keep that in mind. Maybe we can improve this situation by make the resolution more transparent to controller. And maybe we can teach the tool how to resolve conflict similarly to how controller do. And finally, maybe when we involve more controller in the progress of development system, controller may maybe believe more on that one and trust more on the tool because they understand more on that one. So keep that in mind. We think that personalized automation is one of the solutions. Personalized automation means now we build a tool that can customize for each controller, because each of them may be always different, right? So we customize the tool for each of them, and it behaves different for each controller. To do that, we think that we can use the artificial intelligence here to learn controller action and strategy in resolve the conflict. So we call it conflict resolution advisory for controller. So it leads to our research question. First one, is the conflict resolution using the reinforcement learning method? However, to solve this problem, we must investigate two other sub-problems. The first one is conflict detection. And here we focus on the probabilistic conflict detection, which means that instead of in the deterministic or static setting, we consider about the probability of the conflict can happen with uncertainty. And another one is also very important is trajectory prediction. Here we focus on the controller action prediction because we observe from the trajectory data. We observe that controller action can affect and impact the trajectory of the flight. So if we can predict the controller action, we can increase the performance or the accuracy of the trajectory prediction algorithm. So they will have the link together as see on the picture. So if we support each other, and at the end they will have the full conflict detection and resolution advisory. So first we're working with the trajectory prediction. So here is the framework we introduced. In the left, we have two main modules. The left on the right hand side, you can see it's the model for predictive controller action. Based on the trajectory data for set in the center, we can extract the controller action based on the entering point and exit point for each sector. And using the random forest, we can predict that with high accuracy. And then on the left hand side, you can see we formulate another problem. Given the entering position and exit position, we will do the clustering and then extract the nominal root, the virtual nominal root. It's not a similar one with the predefined nominal root, but what we observe from the data. It reflects what the pattern, how the flight will travel throughout the center. So by combining the two models, we have the final 3D, 4D trajectory prediction. And here the accuracy is quite high. Of course, depend on data. For machine learning, it depends on data. Here with the given data, we can predict very high accuracy for vertical and speed. And the vectoring is also with acceptable accuracy more than 72%. However, it's the most difficult action to predict in the center. Next one, we discuss about the conflict detection. So for conflict detection, we have two things. The first one is we will build another trajectory prediction. Now we consider the uncertainty. And the second thing is with the new trajectory prediction with uncertainty, we try to detect the predict the probability of the conflict by using the Bayesian Optimization. So in this case, to model the uncertainty in the trajectory, there are a few work for that, but in our case we use the Gaussian process for this one. However, on the left hand side, you can see here is the uncertainty we learn and then simulate using the Gaussian process, and it failed to capture the variation of the data because normally the uncertainty about position of aircraft will change depending on the position of aircraft. For example, if it goes straight, it's different from it happens at the turning point. However, Gaussian process failed to do that. So we use another updated version of Gaussian process. It's called the Heteroscedastic Gaussian Process. It can have better way to model the trajectory and then capture the variance of the data. So that's what we use for this problem, to learn this uncertainty from real data. And then with that one, with the model for learn uncertainty, we go with another assumption. So to build the trajectory prediction in operation, normally the fly can fly like freely, right? They must go for with some constraint or some demand, like this must go some way, pass by some waypoint, or in maneuver to resolve the conflict, it must pass by some virtual wave position. So keep that in mind, we put some conditional position or conditional point. That the position the aircraft must pass by, and then we filtering some data given that information. And here you can see we have the filtered data. And then we use the reverse model with this one for tuning and training another model we call the predictive model. And on the right hand side you see the result of this one. So the real one is the mean trajectory, is the predicted trajectory that the flight will travel. And on the rest one is uncertainty, the uncertainty that capture the possible position of error over time. So it reflects both things. The first one is reflect the filtered data, and the second one is the full data. So it's a combination of both. After we have that one, we consider about, now we're talking about the probabilistic conflict detection. So there are two metrics we will consider here. The first one is the probabilistic closest point approach. It means at the position that have maximized the probability of conflict between two errors. And the second one is the time to that position. So using the Bayesian optimization, we can quickly locate that position and estimate the time to that position. Here we do the comparison between the Bayesian optimization with the result. The result means you just discrete all the time, and with the different time step, like 1 second, 2 seconds, and then at each position you will check the probability of conflict to identify the time have the maximum probability of conflict. So by comparison to them, and we capture the model performance based on the two metrics, and the computational cost is second. So as the result, you can see on the result here. So the Bayesian optimization can work with continuous time. This means that you don't need to specify the time step for searching. And secondly, it can perform like very well and match it and very close to the result for the rate 1 second. However, the computation cost for that one is around equal to 10 or 30 seconds, and very freely to apply that one. So it also has that advantage of the Bayesian optimization for this one, and it's very easy to extend it into multi-error conflict detection. So however, for this case, we just stop here, and maybe more work should be studied on conducted to make it like for multi-error and put it into the simulator for flight simulator to detect for conflict detection and resolution. The final one is conflict resolution. Here we introduce the reinforcement learning approach for conflict resolution. They have 5 things. The first one is the reason why we use reinforcement learning, the overview, the learning environment, the artificial intelligence agent. Learning environment and AI agent is two main components for reinforcement learning. And finally, the evaluation. So why we need the reinforcement learning? It's a little bit different from the reverse approach, because in reinforcement learning, we do not require prior knowledge of the mapping function between the input and output. We don't need that information. So we will learn it by trial and error. Secondly, the model can self-evolve also by trial and error mechanism when it encounters a scene scenario. So it can learn by itself and improve by itself. And also more important, also very importantly, human reference here can very easy and flexibly implement in this model to capture human reference. And finally, so the knowledge about the environment also required, however, it's also very easy to implement that in the simulator. So the overview is the concept around how we deploy how we get the idea of reinforcement learning. So there are two main components, environment and agent. The environment will have generate the conflict, right? And we call it the state. The conflict will be extract the feature vector, some feature vector, and send to agent. The agent will have some model and make the prediction about what action I should take. And here, for example, here you can see the one possible action. With the action, the environment on the simulator will respond with one reward, whether it's good or bad. And the reward here reflects two things, whether it successfully resolved the conflict and the deviation. Like the bigger the deviation, maybe the slower the score. So it depends. Sometimes the reward, you can call it in another way, the penalty. And it reverts in the meaning, but all of them is acceptable. For learning environment, there are 5 things we should define. The first one is what is maneuver or the action. The second one is what uncertainty you consider in your simulator or in your environment. Next one is the conflict scenario, how you define the conflict scenario. And that's really the most important thing at the stage for the agent to learn. Next one is how to represent that one to machine, because now it's not human to observe and to make decision, but machine. So scenario representation is also a very important one. And finally, the reward function, how to say it's good or bad. So one of the most important things I want to discuss here is the feature vector for the conflict scenario. I call the scenario representation. So here there are three kinds of information I put here for the feature. The first one is uncertainty level of the environment. The second one is the separation status. This means that okay, how the on-ship separate from the other people, the other aircraft, in considering the current maneuver. Like and here you can see the CBA closure, the direction of the CBA closure, and on that information. And finally, we have another one is direction from the return point N to the CBA. So this one I put here to guide the agent about the current potential of the searching direction. If the current direction, searching direction is good, it will decrease the penalty, or if further the CBA. So by observe the current reward, the tendency of the current reward, I can guide the agent to search for better position. So for the artificial and the AI agent, so it's how it looks like. So here you have the agent have two main models. The first one is actor model, and the second one is the predictive model. By the environment will give the agent the feature vector of the scenario, and then the actor network will predict, using that one to predict the action. And the second one is the predictive network will use that action and evaluate that one, estimate whether it's good or not. So the purpose of the actor network is to predict the action, and the purpose of predictive network here is to estimate and to qualify whether our performance of our current model is good or bad. If sometimes you see that okay, the estimated reward very different from the real reward, at that time it means the model is underfit or very bad performance. At that time you must retrain everything. So the predictive network is somehow to keep monitor the performance of the model. So that's how we use this kind of architecture for the AI agent. And here is one learning episode. So in one searching, given the conflict scenario, the agent will try different positions in the searching, and when it's searching, you try to find the position that maximize the reward function. So it's how it looks like. For the training, you can see here is the flowchart for the training. By interaction between agent and the environment, it generates data. Like I see this scenario, I perform that action, and then I receive this reward, right? So by doing this multiple times, you have a data. And we sampling the data and then train the model. That's for training. For testing or for prediction action, we only focus on the interaction, which means now we have the environment generate some conflict scenario, and the actor model here, actor network here will predict the action, and that action may be yet successfully or unsuccessfully resolve the conflict, and that's what the predicted action. And at the same time, I have already mentioned the predictive network will estimate the score for that one and monitor the performance of the model. So for evaluation, we generate a conflict with 4 different range of time to CBA, 6 different conflict angles, and for each group we have 200 conflict scenarios. And we also test with different number of aircraft from 2 to 50, and on different level of uncertainty. 0 means that no uncertainty, and then 10% uncertainty about the position on ship and aircraft. So in total we have 268,000 conflict scenarios for testing. And this is the conversion of the model. After around 2,000 iteration, the model will be converged and it will stable. However, they have effect of the uncertainty. You can see effect of the uncertainty and high traffic and dense traffic to reduce the performance of the model. However, it's still stable. So in average, average reward and successful rate is two metrics we should consider in this work. So for the average reward, the maximum be 100. So in the worst case, 72.5%, and in the best case, 88%. 88 score over 100. And when we consider, we mentioned about successful rate. The success rate here is the score, the maneuver score, which have the score better than 40. It's lower than that, we consider it's not very good maneuver, so we should consider the one have the high score. And so as you can see here, with no uncertainty, it can solve 98% of the scenario. And in the worst case, 81%. One thing you can say here, you can see here, over 90%, it can resolve the conflict over 90% when we have 10 aircraft and in medium uncertainty. So it's quite good if you take a look on this one. So one thing we should discuss here is why the performance of model drop very significant when the density of the traffic increase and uncertainty is very big. Because you can say that, you can take a look and you can see that when the density of the traffic increase significant, the feasible region here, the position of the maneuver in the feasible region is fragment. So it means the position you can put the returning point is limited and very easy to jump from feasible to unfeasible. Infeasible. And so that's the reason why when you have a very high uncertainty, it's very easy to shift the one maneuver from the good one become the bad one. So that's the reason why it's very easy to reduce the performance of the model when we have high density and high uncertainty. So now we discuss the case study for that approach. So we use the same approach to reinforcement learning one with the whole thing, but however now we consider about real data, the controller action. So we use the very simple interactive conflict solver to generate a conflict. So it's to human, and then human can play around and to resolve the conflict. So if they play enough, they can have the action and perform their strategy. We have some strategy and to resolve the conflict. We capture that information, and then we inject that information into the reward function, and then that is somehow it look like the result. It's the result. So on the left hand side, here one example of the stochastic resolution. So this position is the stochastic position given by the not controller but the user, and now it's the prediction of the agent given that information. So you can see it's very close to each other. And here is the 6 random scenario, that unseen scenario, and how it looks like. The heat map here we call the penalty heat map and or reference heat map. So the darker blue here, the smaller number is the better the score. And for the model, you can see the conversion. The model converts very fast, and not only more than 75% have the score less than 100. Keep must remind that the maximum for the feasible maneuver is 1000, so around 10%. So 75 the scenario, the case can predict the maneuver like less than 10% of the score. So it means it can mimic controller with very high accuracy. So at the conclusion, for trajectory prediction, we have extract the controller action from data, predict the flight trajectory, consider the controller action, and then using the heteroscedastic Gaussian process for trajectory prediction with uncertainty. For conflict detection, we use the Bayesian Optimization, and it can quickly detect the potential conflict, assess how severe the conflict is. And finally, for the conflict resolution, we have formulated that problem into the problem using deep reinforcement learning. And then all the components have been discussed, and we also showed that it's very easy to adjust and modify for different configuration or purpose, learning purpose. And finally, we have also discussed one case study using the same framework and also considering controller reference to resolve conflict. So for future work, we have worked more on the strategy reconstruction from the data. Secondly, we should focus more on future extraction or scenario representation to improve the performance of the model, probably conflict detection, and finally the multi-agent conflict resolution. So that's all for my presentation. Thank you.
Thank you, Dr. Pham, for such an interesting presentation. Let's put our hands together one more time to congratulate him. If you like this video, please subscribe to our channel. Thank you.